So what are we trying to find in this one? What's the unknown? The solute, exactly. So I know my percent. Whoops. So I'm gonna take that out of percent by moving my decimal back 2 places. And like Samuel said, the hydrogen peroxide, that's what I don't know. So that's my X. And it says I have 600 liters of a 3% hydrogen peroxide solution. So that's how much I have of the whole solution. So that makes it a little bit easier. That means all I need to put is on this is a 6 on the bottom. So it'll make the math easier. If it would have said 6 liters of water, then that would have been just solvent. You would have had to add solid. So we just do point, bring it up here. So 0.03 times 6 gives us 0.18. And I'm going to add a 0 because I need 3 sig figs. And it's the volume. So since my other volume isn't liters, then this one would be in liters. Okay, so like I said, not tomorrow, what is tomorrow, Wednesday? Thursday, when y'all have a quiz, it'll be a couple of problems from what we did yesterday and a couple of problems somewhere we're going to eventually learn today. But it's not necessarily going to be the hardest problem. All right. Let me close this. And we'll do our quiz. All you need is just a calculator for your quiz. And then when you have a chance to do that, if you will pass it up, we're going to work on our notes. Ma'am. All righty. So we have left with what's called colligative properties on our notes. We're actually at stoichiometry, but we're going to skip that for now. So for the stoichiometry part, you will have to go and watch a video. I have 2 videos posted today. One is for the whole class, like the whole class period, so you don't need to watch that one. The one that's already posted is just some stoichiometry that you need to do for your notes. And then also we're tending to run out of time, so I want some other problems with colligative properties. So you need to watch that by Thursday or Friday. So we'll have a quiz on Thursday, and it'll be a couple of problems from yesterday and then a couple of problems from what we're covering today. So today we're looking at colligative properties, and these are properties that show the solution has different physical properties than just a solvent. So if I looked at water, and then if I looked at salt water, they would have some different properties. They would boil at a different temperature. They would freeze at a different temperature. And these are colligative properties. So the characteristics of a solution that does not depend upon the size of the solute particles, but only their concentration. The physical properties of solutions are different than those of the pure solvent. Colligative properties depend upon the number of ionized particles dissolved in a given mass of solvent. The more particles, the greater the effect. So for instance, the freezing point dropping when you add an ionic compound to it, that's going to be an example of a colligative properties. So adding a non-volatile solute to a solvent results in changes to the colligative properties. And it's because that solute interferes with the pure solvent's phase change. So one thing that becomes important is how many particles an ionic compound will break into, or how many ions, because you'll see in a minute it becomes part of the formula. So like we kind of did when we were doing the molarity of ionized, or the ions from an ionic compound, that's kind of similar to what we're looking at here. So for sodium chloride, neither one has a subscript. So that means when they ionize, I just end up with two particles, one sodium and one chloride. If I look at sodium, sodium sulfate, the sodium has a subscript of 2. So that means I will have 2 sodium ions. And the sulfate, the SO4, that sulfate, that's a polyatomic ion, and it will stay together as just one particle. So I have 2 sodium and 1 sulfate for a total of 3. If my sulfate would have been in parentheses with a number on the outside, a subscript on the outside, then that would have meant I had 3 sulfate ions, but this one only had 1. The next one, I have 2 polyatomic ions actually together. I have ammonium. I have 3 of those. And then I have my phosphate, my PO4, and I only have 1 of those. So I have a total of 4 particles, if that was to ionize in water. So what we see is the polyatomic ions stay together. If I had phosphate, it's not going to divide into phosphorus and oxygen or oxide. It's going to stay together as one ion. Covalent compounds, remember covalent are the nonmetals, at least 2 or more nonmetals, and organic compounds. Organic compounds contain carbon. Those do not ionize at all, and they stay together as just one particle. So let's practice through on a few of these, counting particles. I was doing that for the journal tomorrow, actually, some other compounds. So we'll start with magnesium chloride. So that's MgCl2. So if I put that in water, it's going to ionize into 1 magnesium and 2 chlorides for a total of 3 particles. Iron 3 nitrate, that 3 means that this iron has a +3 charge, and the nitrate is a -1. So when I write that formula, it's going to be FeNO3, and that would have to have a subscript of 3 on the outside. So how many particles do you think that one will ionize into? 4, exactly. 3 of the nitrates and then just 1 of the iron for a total of 4. What about calcium bromide? 2 from the bromides, but then 1 more from the calcium for a total of 3. What about ethanol? And it has the formula right there. Does that look like any kind of ionic compound we've worked with? Remember, an ionic compound is a metal plus a nonmetal. Is that an ionic compound? What is that? Or what kind of compound? Organic compound, because it has some carbon in it. So that's just going to stay as one particle, one molecule. Aluminum sulfate, Al, let's see, 2, SO4, 3. So how many would that ionize into? 5, exactly. 2 aluminum, 3 sulfate, so a total of 5. And then what about dinitrogen pentaoxide? It looks like it would be 7, but is that an ionic compound? It's a covalent, 2 nonmetals. So this is actually just one particle. They stay together. And you'll see in a minute that is going to be part, like I said, part of our formula. So there's more colligative properties that we're going to look at, that we are going to look at today. We're kind of looking at the main ones. Boiling point elevation and freezing point depression. Those are kind of the big ones, and those are the ones that we will work problems with. Yes, it is supposed to say boiling. What am I missing on that? Huh? The I. Oh yeah, okay, sure. I kept on looking at it. I was like, I couldn't figure it out. So boiling point elevation. So that's why we keep, because of boiling point elevation and freezing point depression, that's why we keep antifreeze in our car. A lot of times down here, we don't have to worry about it getting too cold, although this year we did. So the freezing point depression, antifreeze, what it does, instead of it freezing maybe the water at 0 degrees Celsius, it causes it to have to go lower than that before it'll freeze. And then antifreeze also keeps things, if they get too hot, then it also will help with that. Also, freezing point depression is why they put salt on bridges. Water freezes at 0 degrees Celsius. If they're worried about it freezing and getting dangerous for vehicles, they'll salt them. And then it has to go lower than 0 degrees Celsius. And oftentimes we don't get that low around here as far as temperature. Obviously, it was an exception this year. So boiling point elevation is when you add a non-volatile solute and it increases the point at which a solution boils. So if you add salt to your water before you start making your spaghetti, then it's going to have to get a little bit higher than 100 degrees Celsius wherever it boils. So your boiling point is going to increase. Your freezing point will decrease. So it's going to go lower than normal. And like I said, that salt added to like bridges so they won't freeze at a lower temperature. And then lowering the vapor pressure, if you add a non-volatile solute, it will lower the vapor pressure of a solvent. And vapor pressure means how quickly it vaporizes. So if you spill gasoline on concrete, especially if it's hot, it's going to vaporize really quickly. If you maybe had some sand in that gasoline when you spilt it, then it's not going to vaporize as quickly. That sand is going to get in the way of the solvent particles reacting with each other. And so it's going to slow down that process. So like I said, we're mainly going to be spending time on those first two right there and working some problems with those. Factors that affect our colligative properties, the molality, that would be the little m. And as I increase that, it increases, let's see, I shouldn't do two. Increase my molality, then the change, delta, a triangle means delta, which means change, then the change increases. So in other words, if I have a higher molal solution, then it's more concentrated, there's more particles, and so I'm going to see a bigger elevation in the boiling point or a larger drop in the freezing point. Whether the solution is ionic or molecular, we already know that ionic gives us more particles. So ionic has a greater change. The number of particles, and that's represented by an I, a cursive I, like that. If I try to write it here, it all runs together. I know that if I increase the number of particles, it increases the change. In a minute, when you see this formula, you'll see that it's just a plain multiplication. So that's why all of these things are causing an increase. And the boiling point or freezing point constants, which are numbers that are given to you, or that maybe you look up in a table, the larger those are, the more that I'm going to see boiling point elevation or freezing point depression. All right, so let's look at our first one, delta T. So that's change in temperature. And this is when I'm looking at boiling point elevation. So my change in temperature is going to be KB times little m times I. So KB is that molar boiling point constant. And like I said, that's either going to be given to you or you'll see in a minute, there's a little table that would have that listed. M is molality. I is the number of particles. It never gets all the way down to 0. The smallest it can get is 1. So if I do that math, I'll find out how much the change is going to be to that boiling point. So if I want to actually know the new boiling point, I'll have to take my boiling point original and add my delta T, because the boiling point should go up. So like water boils, we're dealing with in Celsius at 100 degrees Celsius. So whatever I found that change to be, then I would add that to my 100 degrees Celsius, and that would give me my new boiling point. My delta T should always be positive because a change is positive. We need to know how to apply that change, but any kind of change, if you think of it like on a number line, a change is always positive. Where the exception to that is in physics, where you kind of have to work with vectors, and sometimes then the direction becomes important too. So for freezing point, it's pretty well the same. Delta T is going to be equal to Kf. That's the only change, times M times I. So this is for my freezing point depression. And then if I wanted to know my freezing point new, oops, yeah, that's freezing, not a B, how about a P for point? New, then I'm going to take my freezing point original and I would subtract my delta T because I want my freezing point to go down. So you're going to subtract your delta T that you calculated. So I know that y'all's little table kind of got separated, like your headings got separated. So if you'll flip the page and add those headings at the top of your chart. So if you'll put solvent over, here they are right here. Solvent over the first column, boiling point, and so forth and so on. Nothing in this table affects sig figs. So like when we were taking stuff off of our pink, like 273 or 1 atmosphere, those are either constants or conversion factors, and those don't affect sig figs. Also, your I in that formula doesn't affect sig figs because that's a counting number. So we may say 1, but really that's 1.000. But you notice these are where you would get your Kf or your Kb, depending on what your solvent was. The temperatures are in Celsius because the Kf and the Kb that we're using happens to be in degrees Celsius. There's probably another table of Kfs where the temperature are in Fahrenheit, but this one happens to be in degrees Celsius. All right, let's look at a couple of problems, and if we run out of time, I finish working these problems on the YouTube channel. along with the stoichiometry, the little bit of stoichiometry that's up earlier in your notes. So what is the boiling point of a solution in which 75 grams of sodium sulfate, there's my formula for sodium sulfate. So I can go in ahead and look at my I, 2 sodiums and 1 sulfate. So my I is going to be equal to 3. Are dissolved in 800 grams of water, and there is my KB. So I need to find my delta T. So I have my KB, I have my I, but what I don't have is my little m, my molality. And in fact, I don't even have my moles of sodium sulfate. So just like we had to do on most of those problems, I'm going to have to convert my grams to moles. So I have 75 grams of sodium sulfate. And it has a molar mass of 142.05 grams per 1 mole. That 75 is 4 sig figs, so I'm going to do this as 4 sig figs, so 0.5280 moles. So molality is moles of solute, which is what I have per kilogram of solvent. So I have 800 grams, which is the same thing as 0.8000 kilograms, which is right here. So whenever I take my top number, divide by my bottom number, I get 0.6600 little m. And I will say that these problems can have quite a few little steps. Definitely not my favorite topic. All right, now I have everything that I need to figure out my delta T, my change in temperature. So I would take my KB, which is in the table and also is right there, so 5.12, times my molality, which is what I calculated there. And then I have to put my I underneath because I kind of ran out of room. My I was 3, sodium sulfate. So I'm simply going to multiply those 3 things together to get my change in temperature. And when I did, I got 10.14 degrees Celsius. So that's how much the temperature is going to change. But this one actually asked me for the boiling point of the solution. So that has to be the new boiling point. So I have to take my original boiling point of water because that's my solvent. So that's 100 degrees. Am I going to add or subtract the 10.14? Add, right, because boiling points elevate. 10.14, and I end up with 100 point, no, not just 100, how about 110? With all the work, I'm going to do the little easiest part at the end wrong. 14 degrees Celsius. Ooh, quite a few little steps. Sometimes you may get like 3 or 4 places behind the decimal with sig figs. Don't be scared if you do, okay? Because you may get may have a large change. Anybody have any questions about any particular step of that? Just quite a few different things put together. All right, so let's take that one out. I think we have time to look at one more. The one below it is pretty similar, except instead of boiling, I'm freezing. And I think I have a different solvent. So what is the freezing point of a solution in which 35 grams of magnesium bromide Always kind of get that out of the way. I is equal to 3 because 1 magnesium and 2 bromides are dissolved in 400 grams of acetic acid. So acetic acid is my solvent, so I'm going to change that to kilograms, just while I'm thinking of it. So I have my KF, I have my I, but I don't have my little m again. And once again, don't even have moles. I'm going to have to do a mole to gram to begin with. 35 grams of magnesium bromide. And 1 mole has a mass of 184.11. That's just its molar mass, 2 bromines and 1 magnesium. 35 divided by 184.11 would give me 0.190 moles. So I'm going toward my little m. So it moles of solute, I've got that, divided by kilograms. And so that's why I moved my decimal over already. So 0.4000 kilograms. Just 3 sig figs because of my moles. It has 3 sig figs. My bottom number has 4, but I got to go with the least. So 0.4475 little m. All right. Woo. All that I needed just to kind of. So now we got to do our delta T. I got to find out what my change is. So that's my KF, which is right here, times my N, which I went to all the trouble to figure out. And then times my I, which was 3. Yes, ma'am. Because it says it was magnesium bromide. Magnesium's a +2 and bromide's a -1. So my formula would be MgBr2. Because when I put that 2 there, then I'll have my +2 -2. So now I have 1 magnesium, but because of that, I have 2. So that's where I'm going to 3. Got my total 3. All right, so what did we get right here? 5.56? Anybody? Anybody wake up? Anybody? Anybody lie? So I get 5.56? All right, so that's my change. So I had acetic acid. That was my original one. So I'd have to go up to that little chart because I sure don't know what acetic acid freezes at. What does it freeze at? 16.6? 16.6. Now, am I going to add or I'm going to subtract that change? Subtract. And some people do all the work and then they'll just get those two mixed up. So freezing point going down, so it would go down to 11.04 degrees Celsius. All right, we'll stop there. And like I said, the last 2 I've worked out on video. And then also that little bit of stoichiometry. There may be one problem on that solution stoichiometry on the test. There's not going to be a whole bunch of it. All righty. I'll let y'all. As long as I need to be. I don't really have anything else to do. I have to do today. Well, I need to go to the grocery store.